Yeah, I went through a kind of a semi-classical topic, but I want to explain maybe a new perspective on this type of compactifications. Okay, maybe I should say the goal is to try to compactify the moduli of vector bundles, not over a smooth curve by letting it degenerate to another one, and try to add some extra degenerate objects to our moduli problem to make the moduli compact. And hopefully, what I will try to explain is if you understand how to do this for vector bundles well enough, then stack theoretically, then it's easy to guess what would be the moduli compactification for gauge maps. So that's going to be the goal of today. Let me just tell you a bit about the setup. So, oh, and I should say this is joint work with Dan Halper-Lesner. So I'm going to fix a few things. Let's start with an arithmetic genus. So a lot of the curves are going to have genus G. We're going to work mainly with vector bundles, so the gauge group is going to be GLN. So we're going to fix a positive integer. Let me say positive. And then the group is going to be GLN. Okay? And then just to have things for later, I'm going to also look at a projective variety. So we're going to fix a projective GLN variety. And finally, to have something connected, or at least of finite type, we're going to fix a degree of a vector bundle. So let me just say an Euler characteristic. Okay, so let me just recall a bit what we know over smooth curves, just to set up, to fix some notation. So let's just remember what happens over smooth curves.
That's a characteristic of what?
Of the vector bundle. So I'm just going to have this data, an integer G, rank, and some Euler characteristic. Yeah. So this is just the degree of the vector bundle, pretty much. But
over X?
No. So X is going to be the target. So I'm gonna explain now what type of things I'm gonna look at. But I just wanted to have this in the board, not to have to repeat it again. But right now I'm gonna explain a bit what type of thing we're gonna look at. So let C be a smooth projective curve. So there's two things that we can look at. I mean, one is a special case of the other. The first thing is to look at just the simplest space of gauge maps that we can think of. This is going to be C into, well, let's make X the target a point, mod GLN. So remember, this is just the classifying stack of Rankin vector bundles. And what we're going to do is going to fix here the Euler characteristic. So by definition, this is just going to be the stack of Rankin vector bundles. E with Euler characteristic time. And this is a nice, this is a smooth stack. It's going to be connected once we fix the Euler characteristic. And what we know is that two things are satisfied. So here we're going to have an HN stratification. Plus we're going to have a semi-stable locus, and that thing is going to have a proper, actually a projective good moduli space. So we're going to have a projective semi-stable moduli. The reason is this thing satisfies the valuative criterion for properness. So you can fill in families over a DVR. That's not too difficult. And then we have this thing that was considered in many talks before, and also Dan told you a bit about it. This is maps from this into GLN, and again we can fix some data of the vector bundle, or even better, if we want a compact thing, we want a funny type thing, we might want to fix some class in the dual of the equivariant neuron subary group of X mod GLN. So maybe you can try to fix. So this is going to be gauge maps with fixed given class. So depending on where you're coming from, you can think about this as some kind of homology, or the dual of just the neurons of every group of the stack. And again, we have the same thing. So we have an HN stratification. And then if you do something here, which is take this gauge and enlarge it a bit, something that I'm going to call MGLN-CX, where you allow your curve to pick up some trees of P1s, then for this thing you're going to have a projective. Space. So I think in Dan's lectures, he was explaining about the affine case. We were going to restrict to the projective case. And there you need to modify the moduli problem slightly, but yeah, and this is the page maps as considered by, for example, so this is the compactification that I think Dan mentioned in his talk. Okay, so this is this is pretty classical. I guess here projective moduli space is due to Schmidt originally, and string stratification that kind of explain how you can get it. And the goal for today is going to be to see what happens when you try to let C vary. So the question is, what happens if you let C vary? In other words, degenerate to singular curves. So in particular, we're going to be looking at nice degenerations, as we were told by in a Mumford, there's a nice class of curves, stable curves, where you have actually a proper moduli space, or even a proper Deligne-Mumford stack. So we're going to be looking at the generations of a smooth curve into stable curves, or even better, we're going to be trying to compactify this type of moduli spaces universally over the Deligne-Mumford stable curves. So let me just tell you an answer to begin with is over another curve. So if you replace C with another curve, then all of these moduli, I mean the first one and certainly the second one, let's say map C BGLN, the stack of curves, does not satisfy the evaluative criterion for properness, the existence part. So, and if you try to build moduli spaces, you're not going to expect your moduli space to be proper. So the goal is, let me say what is going to be the goal today. The goal is going to be to enlarge both of these moduli spaces, both of these moduli problems in order to obtain a compact moduli space. Plus some extra nice conditions that I'm going to tell you about later on. So the goal today we're going to enlarge the moduli problems, and I'm going to tell you a natural way, or like a natural enlargement over the boundary of the Deligne-Mumford moduli space. So we're going to be defining a couple of stacks. One I'm going to be calling MGLN. Maybe I'm going to put a chi. And then we're going to consider M GLN X beta. And these are both going to live over the Deligne-Mumford compactification. So the Deligne-Mumford stack. The fibers over smooth curves are going to be these moduli spaces, which is the moduli of vector bundles on the curve, and the moduli of actually this type of glitch maps. And then hopefully by the end of the talk you will know what one natural thing to try to do at the boundary in order to get proper moduli spaces. So both of these maps are going to satisfy the evaluative criterion for properness, and you're going to have a natural stability condition, and you're going to get proper moduli spaces. So you also have Harder-Narasimhan stratification, so you have access to the powerful tools of theta stratifications to integrate like getting indexes of K3 classes over these moduli problems. So we're compactifying maps into these Artin stacks in some way, kind of trying to count how many nodal curves, or like how many curves of a given genus there are inside these things. Okay, so let me just say that some work, we're going to get some moduli spaces now sitting over the Deligne-Mumford moduli space. And generally I'm going to denote with mathcal letters stacks, and I'm going to denote with Roman letters moduli spaces. Okay. So this is kind of a classical story, how to compactify this. I'm going to explain a bit of the history of this and a few of the approaches. I'm going to give a new perspective of how you can think about these compactifications, and that allows you to also get the glitch maps, which, as far as I know, it's a new construction in rank bigger than 1. So when your vector bundle the n is strictly bigger than 1. So are there any questions about what is the goal and the setup?
What is the difference between the Roman M's and the
Sorry, these are moduli spaces. We're going to get proper moduli spaces.
You mean ETH? Are they different from the ones on the left?
These are stacks, unbounded, very, very large.
I see, so the ones on the right have some...
a semi-stable locus, you're going to have a stability condition, the same as for vector bundles.
I see, so the ones on the right are semi-stable.
Yeah, so you should think this is the stack of vector bundles. But this is going to be a smooth, connected stack. This map is going to be flat, Cohen-Macaulay or something. But inside you're going to have an open thing of semi-stables. This is not going to admit a good moduli space, but inside you're going to have a thing of semi-stable ones that is going to have a moduli space. So if you want, I can put here semi-stable to make it more clear that this is, we're cutting down, so using some semi-stability.
The scheme or the stack?
This is a stack.
On the right-hand side.
On the right-hand side. So in a priori, these are algebraic spaces.
Okay.
They are candidates for line bundles. I mean, this is projective. That's for sure.
I mean,
This one, the way we built it is a priori an algebraic space, but there's candidates for like a line bundle that you can descend.
But it's not parameterizing, it's parameterizing S equivalent classes.
Yes, that's right. Yeah, they are. Yeah, I mean properness. It somehow contains separatedness in it. These are not big stacks. They are algebraic spaces. Yeah.
What's written over the arrow that goes from left to left?
Oh, work a bit. I'm gonna explain hopefully what type of. I'm not gonna explain the word that goes from here to here. I'm gonna explain the word that goes into setting up this moduli problem, and then there's these stack theoretic techniques that Dan explained a bit about. Maybe I can say a bit about how you go from there to the Hardener Riemann and the moduli space. But I think like the most important idea actually is how to understand these spaces well enough to set up this machinery. That's what I'm going to be trying to do. Any other questions? Okay. So, okay, so let me just tell you, most of the time I'm just going to be focusing on the left. I just compactify the moduli of vector bundles. And then the gauge maps, they are going to drop out of the construction. So there's not going to be much more work involved to do it in more generality. It's kind of nice. Okay, so let's do vector bundles. There's basically two approaches to compactifying, well, two main approaches in the literature that I know of compactifying vector bundles over nodal curves, or over the Deligne-Mumford. So the first one, I guess in this context, is Vipande, building on work of Maruyama, Gieseker, and Simpson. So this is using torsion-free sheaves. So you do, let's say that you have this Deligne-Mumford stack. We're going to be working over the universal curve, over the Deligne-Mumford stack. So this is going to be the universal curve. Sorry, that's kind of tiny. And what we want to do is there's a stack of vector bundles of this relative morphism. We want to throw in some extra objects. And something that you can do is you can also allow torsion-free sheaf. So you can allow your vector bundle to degenerate into a torsion-free sheaf. So there's this stack called TF of torsion-free sheaves. I mean, every time I say stack, you can think of the moduli problem. So you have this moduli problem of torsion-free sheaves over this universal curve. Really, it's over the morphism. And maybe you can throw in a chi. I'm not going to throw in the chi. This admits a map into this Deligne-Mumford stack. And the fiber over a curve is just going to be the moduli stack of torsion-free sheaves on that curve. And the good thing about this is this certainly this satisfies the evaluative criterion of properness. So this is just classical going back to Langton. You have a nice condition of semi-stability. You can do Gieseker semi-stability, for example, with respect to the natural ample line bundle on this. I would say for our purposes, this thing has two disadvantages. So disadvantages. The first one is torsion-free sheaves. The deformation theory is not that nice. So the formation theory is a bit worse than for vector bundles. The second one I think is a bit more insurmountable, which is if we want to do gauge maps, we want to have a notion of associated fiber bundle with fiber X. in order to know what it means to have a section of the fiber bundle. If you have a vector bundle or a GLN torsor, we know what it means to have an associated fiber bundle. For torsion-free sheaves, it becomes a bit more difficult to see what the analog of that should be. So it's difficult to generalize. To gauge maps. So what we're going to do is we're going to do some kind of resolution of singularities of this stack. And we're going to consider a different moduli problem that actually parameterizes vector bundles. So here's what it is, the second version. I'm going to put a few more names here. So here are the names. Second version. I think in the rank 2 case, it was originally proposed by Gieseker, and Nagaras and Cesari did it in the higher rank for very specific degenerations of curves, and as far as I know, the state of the art using GIT is Schmidt, who did it over the Deligne map for compactification. What you do here is you compactify by allowing or semi-stable as opposed to stable curves. So this moduli is not going to parameterize vector bundles on your fixed stable curve. What you're going to do is you're going to take your given stable curve, C stable, and you're going to take some semi-stable curve with that given stabilization. And how this is going to look like is you're going to take the same curve as before, but you're maybe going to allow a few chains of like a few P1s to appear in between the nodes. So these ones are going to be P1s. It's a shame that I don't have color chalk, but it's the same curve as before, but now you blow up the node a bunch, and you're going to get 3 P1s in between. And you're going to have a vector bundle here. Okay, so our immediate goal is to understand why this is going to be proper. The usual arguments are a bit tough using resolution of energy for surfaces in a sense. So I would like to give a simple explanation of why you would expect that thing to satisfy the validity criterion for properness. I'm going to give, of course, a formal definition of the stack, and then hopefully I'm going to explain why you can set it up in a way that is amenable to the stack theoretic techniques that Dan was telling us about in his course. But the good thing there is you have vector bundles over nodal curves. So the formation theory is easy. You can deform vector bundles on any curve, really. And it makes sense to say what a gauge map is here, right? You can form the associated fiber bundle and take a section. Semi-stability, or what the stability conditions are in here, are a bit more subtle. So I think that's kind of the main point of how do you enlarge gauge maps. But this is going to come later. Okay, so let me define for you more formally what this moduli problem is. So here's the definition. And I guess I was calling in MGLN. So this is the stack, or the moduli problem. Tautologically, you can think about it that way. Parameterizing the following. So it parameterizes pairs, as we have there, of a curve and a vector bundle. So let me tell you what type of conditions we impose. So first, this is a nodal curve. So let me just see a pre-stable curve. Generally a pre-stable family of curves, but let me just tell you what the points are. So it's a nodal connected curve that is going to be irreducible. And of genus G. So we're going to fix the genus that we have from before with stabilization something. We don't really care what the stabilization is, but we're going to assume that the stabilization also has genus G. So it's just a pre-stable curve, any type of nodal curve you like. And then you're going to have a vector bundle. Satisfying the following. So I distilled kind of some of the conditions. They're expressed in a different way in the GAT setup, but I hope you will understand why I'm writing them in this way. I mean, they don't really consider a stack, but if you look at the papers and you squint, you see this stack kind of. So the first condition, and this is the crucial one, this is the insight of Nagarajan and Seshadri, this push forward, where you take your vector bundle on the curve and you push forward to the stabilization, this is going to be torsion free. You're going to have a second condition, it's kind of a positivity condition. This unit, so it's kind of global generation. The unit of this morphism is surjective. This is basically just telling you that you have a vector bundle, you restrict to its P1. In each P1 you're going to have a direct sum of line bundles. All of these line bundles, they are of the form ON. All of the ends appearing should be non-negative. That's what this is saying. But I prefer to put it this way, you'll see why. And finally, you have kind of what I'm going to call the conceived stability condition. This is going to be the determinant of this vector bundle is phi ample. Okay, just some conditions on the pair. So now, what I want to do is to explain what this has to do with conceived stable maps. It's not clear at all why I'm calling this a conceived stability condition, and how, once you interpret it in the right way, the gauge thing drops out. I mean, this also gives a way quicker construction of the GAT setup. But, as I was saying before, this, like in the case where you have a point, no gauge map, this was already kind of under different constructions and so on. Okay, so I want to bring to your attention that there's a clear map from this thing into torsion-free sheaves. So here, the stack of torsion-free sheaves over the dilemma for space, this is going to parameterize pairs of a stable curve and a torsion-free sheaf. So you let the curve vary and you let the torsion-free vary. And there's a way of starting with this data and obtaining a stable curve and a torsion-free sheaf. Well, you just look at what we have, and what you're going to get is some kind of forgetful functor, where you take an element of this moduli space, and you're going to push forward everything to the stabilization. So you're going to take your pair, C and E, and you're going to map it to C stable and the push forward of it. And now I'm already in this situation where I already have enough notation to state the main theorems, at least for the case of vector bundles. So here's the Here's the main theorem. So anytime I say theorem, it's going to be due to both the ongoing work that we have on Dan Halper-Leisner. So this map, first of all, let me tell you a bit about properties of the stack MGLN. MGLN, and let me just restrict to the part that has the given Euler characteristic. So where E has a fixed Euler characteristic, this is a smooth connected stack. It's going to be nice. In the covariant case, we're going to get smooth total moduli spaces, and they're going to map to the Riemann for space. And this map is flat. So it's a nice flat degeneration of the usual stack of vector bundles. The more important theorem is this thing is proper and representable. So what we're doing is we're taking the first compactification in terms of torsion-free sheaves, and we're kind of resolving a bit the singularities. It turns out that this gives you a bit of mileage. So we want to build a stability condition, and if you were, you remember what some of the lectures that we had the previous days, one way to build a stability condition on a stack is to fix a line bundle in here. So okay, what should we do? Well, we have a nice notion of stability here. It's Gieseker semi-stability or Gieseker stability, and then we have this proper one. So the obvious candidate for a line bundle is the following. We can, so line bundle, what we can do is we can take some pullback of some line bundle that gives Gieseker semi-stability, and it's going to be asymptotic stability. So let me just put a family of line bundles to be, this should be an F, to be completely honest. And then we're going to add a small perturbation of a line bundle that is relatively ample for this morphism. So we're going to fix some line bundle. I'm going to suggestively call it L Kontsevich, or maybe L Kornarva more appropriately. And this is going to be very ample, F, very ample. Or F ample, actually. That's good enough. And we're also going to have a family. So eventually over its bounded substack is going to be very ample. So let me tell you a bit about these things. So this first one is due to a project that we had with Fred Leisner, myself, and Trevor Jones. There is a line bundle that recovers Gieseker semi-stability for torsion-free sheaf. So there is. And it's suited for the techniques of infinite dimensional GIT using the affine Grossmanian that Dan was telling you about. So there exists a Gieseker in this type of torsion-free sheaf that recovers Gieseker semi-stability. I mean, if you're paying close attention, I'm saying Gieseker semi-stability, but I'm not telling you a polarization. So I'm going to take the natural polarization on the universal curve. So the canonical is ample. So I'm just going to take
use a line bundle over the stack of.
Oh, yeah, I forgot to say peak. Thank you. That's right. That's a line bundle. Yeah. Yes. So we're going to put that back. We're going to take a line bundle that I'm going to explain next, hopefully, and then we're going to build a numerical invariant using that. And then the next theorem, which is, I guess, the main theorem, is the numerical invariant. Mu, where you take the weight of this line bundle and you divide by kind of like a norm you can do the same norm pretty much. It's using ranks of I mean, a filtration of this is going to be a filtration of the vector bundle in some sense. You need to prove that, but really it's a filtration of the torsion free sheaf. And you can use the ranks to build some kind of like quadratic form, like in the lectures. So you can define this numerical invariant. The most important part is the line bundle, and this determines a theta stratification. So you have Hardener-Riemann theory for this enhanced moduli space, or enhanced moduli problem, plus you get a proper good moduli space. Which is still flat over the lemma for moduli space, satisfies some nice conditions. Okay, so these are kind of the main theorems for vector bundles. During the rest of the talk, I'm going to explain the reason why all of this works. And it's I want to focus on one specific idea that I think explains why, hopefully sheds some light on why you're considering this type of moduli problem and how to generalize it. So let me tell you, this is the punchline of the talk. The reason, and this is the new perspective. The fibers of this map MGLN chi to torsion free sheaves of pushing forward the vector bundle. These are relative Kontsevich stable maps. So stacks, relative stacks. In this case, they're going to be schemes, but that's just that's just a coincidence. Stacks of Kontsevich. Sorry, I don't know how to spell. Stable maps. Into what? Well, I'm about to explain what it is. But it's some kind of universal way of. It's a space that is going to give you a kind of functorial minimal way of blowing up a variety, or like one of these curves, in order to resolve the singularities of a torsion free sheaf. So this is kind of I would say the main idea. Kind of like a question that I'm about to answer is, suppose that I give you a projective variety, you can take it to be smooth even in higher dimensions. And suppose that I give you a torsion free sheaf, so it has some singularities, it's not a vector bundle. Is there a minimal way or a functorial way of blowing up this variety, such that the strict transform becomes a vector bundle? So this work by Renaud and Gruson that tell you, yes, you can certainly do this, but they don't tell you, they just tell you there is a blow up. Is there a functorial way of doing this? Well, actually in this case, there's a cheap way of approaching this. So let's study the fibers of this thing, of this map. This is kind of the main goal that we have right now, understanding this map. So we're going to take a pair in here. It's going to be a stable curve and a torsion free sheaf. And it's going to be a geometric point of this. So it's a torsion free sheaf on a stable curve. And what we want to do is to resolve to a vector bundle. So we want to take this torsion free sheaf in here, kind of blow up a bunch, get some extra P1s, take the strict transform, and hopefully that will become a vector bundle. How do we do this? Well, here's a cheap way of doing it. So actually the Wiener-Gratz and Cesari proof properties is for in the case where you have an irreducible, so they can manage an irreducible curve with a node, and they understand very well versal deformations, how these degenerations of vector bundles turn into torsion free sheaves. And by working locally, they cleverly tell you which blowups you have to do. But what I'm about to tell you is you can be just lazy. You can just take kind of the naive way of resolving these singularities, which is the Grassmannian. So maybe for this talk, I'm going to call it the Renaud-Gruson Grassmannian. But really, this is just a quote scheme. So this is going to be a scheme over the stable curve. It's going to be a quote scheme for, you know, it's something very easy. It's like you just take the identity from the universal curve, like, sorry, from CST to CST. And you're going to want to resolve this and maybe to have rank n here. So just as a reminder, this quote scheme is going to parameterize the following. It's going to parameterize rank n vector bundle quotients of F.
So what did you write? A subscript of what?
Subscript with, oh, here.
Yeah.
Yes, it's a CST
Yeah.
over CST. It's the identity morphism. Generally for quote schemes, you can do relative to a base. This is the identity morphism. So it's kind of the easiest projective morphism you can have. The base is equal to the source. So I think a picture is way more telling than this functor description. So let's take a curve, and let's take so this is CST, and let's take a torsion-free sheaf, which hopefully, secretly, we want it to be the push forward of our vector bundle. So how does this GER RGF look like? Well, so away from the node, this thing is actually a vector bundle of rank n. So there are not that many rank n quotients of it. This is itself. So this space away from the node is going to be an isomorphism. So by the way, this is going to admit a map to CST just by here. So away from the node, this is going to be just the identity. What happens at the node? Well, so your F is going to have some fibers. All of these things are going to have rank n, but when you go to the node, because it's a torsion-free sheaf, your rank is going to jump by something. And what this space looks like is you take the same curve right here, and everywhere away from the node, you're going to have the Grassmannian parameterizing rank n quotients of a rank n vector space. That's just a point. But at the node, you're going to have a Grassmannian parameterizing rank n quotients. Let me draw it a bit more. Rank n quotients of an n plus k vector space. That certainly is not trivial. So this is the functorial way of resolving these singularities. You take this space right here, and you're going to have a Grassmannian of n in n plus k. And this maps right here. So that Grassmannian is going to be contracted. And how do we try to resolve this? Well, this is what I can do. I can take these 2 points, and I can join them inside the Grassmannian by a bunch of P1s. That's an easy way to resolve, to get like a vector bundle there. And by definition, this thing is going to have, so let me call this map F, this projection, or maybe pi. This projection is going to have a universal, a universal vector bundle, rank n vector bundle quotient. That's just by the definition of the space. And what I want to think about is I want to think about this CST. And I'm going to have another curve, C, that is going to be this thing. It's going to be the curve with the chain of P1s. And it's going to map to this, sorry, the blackboard is getting a bit messy, to this Renault Gruson, where am I putting? Renault Gruson space, and then you can take the projection. So I want to do this in the minimal way. So first of all, here's a chain of length 3. I don't want to just throw here a chain of length 1, 2, 3, 4 and contract one of them. So we want to avoid this where one of the chains contracts to a single one, because then we might as well have contracted this chain and it's kind of extraneous data. So what I'm going to do is I'm going to require that this thing is actually, these curves are actually embedded into the Renault Gruson space. If you think a bit about it, this just means that this map is Kontsevich stable. So if we want to do it minimally, what I want to impose here, of course in this case with P1s is kind of like stupid, but I'm going to impose that this thing is Kontsevich stable. On the other hand, the type of curve that I want here is I want to take this modification, and when I project it using the composition, I want the two components to go to the two components and the big ones to shrink. So I want, let's call this phi, suggestively, and what I will want is I will want the push forward of the fundamental class to be the fundamental class. Using these definitions of gauge maps, then this is very familiar to you. So this is what we're going to do. So let me tell you a bit more about this. So the main idea is very simple. You just use this Grassmannian to resolve your thing. But for some reason, I don't think people were thinking about this modular space in this way. So it's actually consecutive stable maps into one of these weird Grassmannians, where you put Grassmannians between the nodes. And this works perfectly well in families. So let me tell you, where am I? Okay, we're good.
Can I just ask a question? So if I take a vector bundle that comes from a map to the Grassmannian, and I do the Kontsevich limit as a stable map to the Grassmannian, is the whole picture compatible with that? I mean, just thinking of the Grassmannian as approximation to BG.
The Grassmannian is an approximation to BG. Wait, can you repeat your question? I'm not sure I understood.
So if I have I can approximate BG by finite dimensional Grassmannians, right? So if I have a sequence of curves with maps to the Grassmannian, I could take their Kontsevich limit, or I could take the limit in your.
Oh, yeah, that's right. Yeah.
And it's the same, more or less the same thing, is it?
Well, wait. These stacks are not separated. So
They're separated once you impose the stability condition.
Once you put the stability condition, the good moduli space is, up to S equivalence. So I'm not sure. You mean do you get the same S equivalence class, or do you get the same stack?
The same S equivalence class and all that.
I can tell you this. You get the same stack. So Schmidt does semi-stability using Grassmannians.
Yeah.
And he does analysis of semi-stability there. So I can tell you the following: the semi-stability that you get dropping out of theta stability using the coordinate line bundle for Kontsevich stable maps is going to be the same. So yes, the stack is going to be the same, although the limits are not unique. So I'm not gonna. But the limits that you can get within the stack are going to be the same. Yes.
But Schmidt uses a different space, right? Your space is a resolution of his, right?
Well, so Schmidt doesn't do torsion-free sheaves. He does this Giesecker type compactification.
Yeah.
It's a bit difficult to see what Schmidt does GAT, right? So he doesn't start in this stack. He starts on some quote scheme, and then he takes some Grassmannians, products Grassmannians over it, and you can embed this stack as a locally closed substack of that. And it turns out that if you do GAT, somehow the semi-stable locus agrees. But the space is very different because the actual parameter space is not going to parameterize these nice things. I'm just doing everything within the stack. I'm not projectivizing and doing GAT. I'm working within the stack. Everything already is nice. It's like an element of this modular space. Whereas for him, you get stuff in the boundary, and the way that you get projective is that by magic, the semi-stable locus happens to coincide with the semi-stable locus of this bigger projective thing. So that's how you get properness there. Whereas here, properness is just properness of Kontsevich stable maps. You fill in the torsion-free sheaf, and then Kontsevich stable maps are satisfy the evaluative criterion. So you can fill in the family. It's a bit of a different argument of why properness is satisfied. But you can see this directly at the level of moduli problems. Sorry, I don't know if I answered the question or not, but hopefully. Okay, so let me just tell you the things.
Unless you're almost finished, speed up.
Yeah, sure. Okay, so let me just say maybe two things. So maybe let me just say NS2, the fact that the community is surjective gives you that you can take one of these modular problems that I said, like an element of the modular problem that I said, and that you can get a surjection like this. So you take the push forward, you take the pullback, and you get a surjection into a vector bundle. So NS2, this global generation, gives you a well-defined map into Kerr. NS3, this determinant condition, if you think about what is the ample line bundle on the Grassmannian, this is exactly telling you this conceived stability. So I'm going to sweep a bunch of technical details under the rug. This not really the moduli space is not literally conceived stable maps, but it's going to be an open and closed substack inside of it. So it's going to be a nice component inside, and it's going to be one of the connected components. And let me just conclude by saying that if you know now this description, then it becomes clear what to do for gauge maps. So gauge maps, let me just finish if you allow me. The definition for the gauge maps, at least like a bit quick, is so now you have this relative Renault-Grusson Grassmannian, or whatever you want to call it, a quote scheme. You can take the modular stack of torsion-free sheaves, or you can work in families. You can take this Grassmannian. And over this Grassmannian, you have this universal vector bundle, Q universal. So let's just modify this picture a bit. Instead of taking a map into that Grassmannian, I'm going to take a map of as follows. I'm going to take a map. So I'm going to have this Grassmannian. Grassmannian. Here I'm going to take the universal GLM bundle, and I'm going to twist it by the projective GLN variety that we have. And then what I'm going to do is I'm going to take a conceived stable maps, a family of conceived stable maps into this thing, satisfying the same conditions that P push forward of the fundamental class is going to be the fundamental class. And it's not difficult to see that this thing is going to satisfy the evaluative criterion for existence of the evaluative criterion for properness. I'm going to record that this is conceived stable. And if you can work out what this means concretely, this is going to parameterize a curve with a vector bundle and a section of the associated like fiber bundle over the curve, and then like you're going to have some stability conditions coming from like the push forward being torsion free, and then you're going to have like the pullback, a combination of the determinant line bundle and the pullback of an ample line bundle coming from X being positive relative to this stabilization morphism. So there's a concrete description of what this modular space is going to be, but I thought it's easier to see what's going on if you think about it in the but I mean, actually the way to guess, like the way to determine what the space should be is by thinking about it this way. So as far as I can tell, this is like a new, I don't think there was a proposal of how to compactify these gauge maps over novel curves. So now you get this thing, it satisfies the Hardener Riemann, you have a very good modular space, so it compactifies maps from curves into X mod GLN. Right, so I'm going to leave it at that. Sorry for going slightly over time. I'm very sorry. Yeah, thank you.
Now there's coffee break, and maybe this will be the moment to ask questions to Andres. And we resume at 10 minutes past 10. Again.